I'm Ruslan Nikolaev from Penn State. In my today's talk, I'm going to present a family of fast and memory-efficient lock and wait-free reclamation. This work is done jointly with Binoy Ravindran from Virginia Tech. So, non-blocking data structures is something you probably heard about, right? So they gain in more traction, more popularity because typically they provide better scalability, they provide better latency guarantees, and more stricter theoretical guarantees. With non-blocking data structures, we don't actually use mutual exclusion. So that means a concurrent thread may hold a pointer to an object which is about to be deleted. So basically, a thread holds a stale pointer. We have to deal with this situation very carefully. And for this purpose, there is a number of algorithms exist called safe memory reclamation. And we typically use them in C and C++ code. So now with garbage collected languages, you may argue that you don't need that, but there is still, I guess, the overall problem is still relevant because even in garbage collected languages, perhaps you want to have some lock-free garbage collector, wait-free garbage collector, which might be even harder. Let's take a look at the problem. Let's say thread B wants to delete an object referred by pointer P. So then we have thread A and thread C trying to dereference this pointer a bit later. Because they are concurrent threads, it's really kind of, there is no mutual exclusion, so they can still potentially access this pointer. So obviously that's going to be a problem. So now, what is the solution to this problem? Well, the solution to this problem, generally speaking, is to just postpone the allocation, to say, okay, let's delete object referred by pointer P only when it's safe to do so. But the problem with this is that we cannot really postpone the allocation indefinitely. Because if we do that, then how can we guarantee non-blocking progress? And it may not be obvious immediately, but typically memory reclamation goes hand in hand with non-blocking progress guarantees. More specifically, if we postpone it indefinitely, we may run out of memory, right? So, and then can we really say that this algorithm is non-blocking? If we exhaust memory, the program crashes, so the algorithm becomes pretty much blocking, right? Even though it may not necessarily use locks. Because this definitions of non-blocking progress is much stricter than just whether I'm using mutex or whether I'm using something else, right? So by the way, regarding non-blocking progress, there are three types of non-blocking progress that researchers typically consider. Abstraction-free, that means algorithms guarantee that a thread makes progress in isolation. So that means if I deschedule a thread, deschedule all other threads, and this thread is running, just one thread is running, so it should be able to make progress. So obviously this is not necessarily good because such situation does not exist in practice. We always have multiple threads running simultaneously, and abstraction-free algorithms are basically prone to live locks. So this is why we have lock-free algorithms. So lock-free algorithms is typically something that is more used in practice. They guarantee that at least one thread makes progress in a finite number of steps, no matter what. So that means even if some thread is preempted, let's make an analogy with blocking algorithms. In a blocking algorithm, one thread that is holding a lock is preempted, then it's other threads are unable to make progress, right? So in this case, at least one thread is still able to make progress, no matter what. So obviously, this may not be enough because with lock-free algorithms, we still have a problem of starvation. So we may want to have wait-free progress. So in wait-free algorithms, all threads make progress in a finite number of steps. So, and obviously wait-free algorithms are harder to design. And, so those are kind of crown jewel, right, of the concurrency, so to say. So another thing regarding memory reclamation is that this is what we call workload balancing. So typically, the way that it works in typical SMR, most basically threads that only make a modification will be deleting nodes, and and consequently they will be checking whether it's safe to delete this node. But this is not necessarily a good strategy, especially if you have some sort of read-dominated workload where most threads are doing some read operations, but only maybe some threads are doing write operation. So it's not completely read operations. They still have write operations, but you have only a small fraction of write operations. So in this case, we may kind of delay reclamation significantly. So by the way, this issue did not exist like with more classical approaches such as reference counting. So with reference counting, log-free reference counting, effectively an arbitrary thread would end up deleting an object, and consequently that can be a read thread or write thread. It can be any thread, right? So, but this is not the case with most SMR schemes that exist today. But why don't we use reference counting? Well, reference counting is impractical due to high overheads. For every object, we would need to have a memory. To access every object, we would need to have a memory fence. We would need to increment the counter and so on. So recent work, which is also our work, Hylene published in PLDI 2021. So in that work, the idea was to use reference counting only when effectively deleting or what we call retiring an object. So retiring means marking an object for deletion, but it's not yet fully deleted. So the idea is that with Hylene the Hylene pretty much showed a good result and relatively small overheads. But with Hylene, we were able to protect against stall threads. That means threads that are preempted. They will not cause any issues. However, strictly speaking, we cannot really say that Hylene would always use unbounded memory, right? So the reason for that is that, let's say we have a situation when some thread is iterating through some list, and another thread keeps adding new nodes and new nodes to that list. So you will never be able to kind of complete this operation. So this thread is starving, so it would reserve more and more memory blocks, and eventually you can say, oh, that's unbounded memory usage. So in this work, we kind of trying to solve this problem. And we not only solve it in a sense that we are creating a fully log-free scheme like the one that will be log-free under any circumstances, but also we provide a wait-free scheme. So we have Crystalline L, which is guaranteeing log-free progress under any circumstances, Crystalline LW, which will be wait-free in some cases, but not in all cases, and Crystalline W, which is wait-free in all cases. So just to compare Crystalline with respect to other existing schemes, let's take a look at this table. So the traditional approaches, such as epoch-based reclamation, that is blocking under any circumstances. So now, if you look at hazard pointers, that's another classical approach. If we allow restarts of the operations, then we can say that this scheme is wait-free. If we don't allow restarts and just say, You have to complete an operation. The operation cannot be broken and you cannot roll back and go back to the beginning of operation. So you are not allowed to restart it. So then it's only lock-free. So now there were other recent papers, such as hazard errors, HE, on this table, which promise to have the same progress guarantees as hazard pointers. However, in our paper, we discussed that it's not quite true. And more specifically, the difference exists if you use one data structures versus multiple data structures. So the problem with multiple data structures is that if we have, from the point of view of one data structure, you may still have, you may still not achieve a lock-free progress or wait-free progress because no threads making progress for this particular data structure. So maybe overall in your system you're making progress, but for this particular data structure you are not making progress. So therefore, there is a distinction between one data structure versus multiple data structures. So with multiple data structures, hazard errors is going to be blocking, right? So that's the difference between hazard pointers. So hazard pointers doesn't have this issue because of some locality of the operations, so that it still checks pointers related only to this particular data structure. So therefore, it will be able to avoid this issue. But this is a very subtle distinction which was not brought into attention in the past, which we mentioned in the paper. So, High-Lean from PLDI24 was lock-free if you use it for one data structure or with restarts, right? So, but otherwise, we cannot really say whether it's lock-free or wait-free because it can potentially use unbounded memory. So with Crystalline L, we can solve this problem with one data structure. So it's going to be lock-free. And with restarts and without restarts, doesn't matter. So with LW, it's kind of similar to hazard errors. So we have wait-free with restarts and lock-free without restarts. So now the question is, how do we solve it for multiple data structures? So now another paper, VFE, wait-free errors in PPOP 2020, extended hazard errors to make it wait-free. So all threads will collaborate with each other to guarantee wait-free progress. So in this case, we can say because all threads collaborate, so this progress guarantees will be attained even for multiple data structures. And that's the similar progress guarantee that we achieve in the most advanced scheme that we present in the paper, Crystalline W. So it's going to be wait-free under any circumstances. So just a little bit of background. High-Lean, in High-Lean threads, explicitly annotate each operation. So they will say, okay, this operation starts, this operation ends. Then you will wrap pointers in a special operation, and that's pretty much what it is. So when you free in an object, you're going to call a special retire call. You will not call delete or free because you cannot immediately delete this object. So the idea in High-Lean 1S was to protect against stall threads. You use some birth error. So whenever you allocate an object, you would associate it with a birth error. And by using this effectively timestamp, or like maybe not precisely timestamp, but whatever the counter is, right? You will be able to protect against situations when a thread is preempted, but then you still use unbounded memory, right? So that will not happen, and that is something that we still use in our approach. So now the key difference in Crystalline L compared to High-Lean 1S that was presented in the PLDI 2021 is its API, right? So its API is more similar to hazard pointers. So why is hazard pointers lock-free or or wait-free, right, under some circumstances? Well, the reason why is because it guarantees that it only has a certain number of local pointers that each thread can hold. And therefore, you can always find a precise memory bound in the worst case scenario. So that means no matter what happens, whether the thread is starving, stalled, you always use a bounded number of memory objects. So effectively, in Crystalline, we modify this special operation that wraps pointers such that we would identify each local pointer by its index, and it will identify just like hazard pointers. You'll have indices from 0, 1, 2, 3, and so on. You will say, okay, that local pointer is 0, that local pointer is 1, and so on. So that way, protect will only reserve a bounded number of pointers for each thread. So otherwise, it's kind of similar. We have retire, marking an object for deletion. Clear will clear all previous reservations, and allocate not a special kind of wrapper for malloc where we also initialize the birth error. Okay. Well, I still have like 4 minutes, right? Okay. Oh, okay. 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 Yeah. Okay. Let me. So in Crystalline L, basically another big difference compared to Hylene is that we use dynamic batches. So effectively, we can accommodate. We don't need to accommodate for the worst case scenario how many objects we need to accumulate in a batch before we can retire. So in Crystalline L, we use the trick which allowed us for the algorithm to still be correct, but retire much sooner. So that's what we call dynamic batches. So now, with respect to wait-free challenges, there are two things, right? So one thing is that protect has an unbounded loop, and the other thing is that that's kind of similar to hazard pointers or hazard errors, and that for which we use a similar approach that was used in wait-free errors. And the other problem is that retry has an unbounded loop. So basically, we had to solve that problem. So we rely on hardware instructions such as fetch and add, or double with cas, and both of these instructions allow to help to solve the wait-free consensus. So they are widely available in ARM and x86. So we don't really. Although they are not available in all architectures, but at least. At least they are available in widely used architectures. So in Crystalline LW, we effectively solve the problem with retire and its unbounded loop. So in the paper, we go into more detail how we do that. With Crystalline W, we effectively had to make protect operation bounded. I think this is one of the most difficult problems. The first problem was relatively easy with as long as you can use hardware swap instruction. With the second problem, we had to use wait-free errors approach, and it's pretty much kind of follows the same idea. But also, it kind of diverged significantly because we only can do retirements once. We cannot go back, unlike wait-free errors. So there is a possibility if it failed, you can kind of try again and try again. Here, you have to do it in one pass, pretty much. Therefore, a number of tricks which we discuss in the paper were adopted for that. So just very quick, I'm going to show a couple of results. We evaluated scheme and compared against Hylene hazard errors, epoch-based reclamation hazard pointers. So for read-dominated, there is read-dominated write-intensive workloads. You can see in both cases, Crystalline performs pretty well I mean, sometimes it can be slightly slower than high-lean because the protect operation is more expensive. But overall, it's kind of comparable. And more importantly, like when you see like oversubscribed scenarios, like after 96 threads, it can still maintain pretty good throughput and even better than high-lean. And yeah, so and this is for both Crystalline W and Crystalline L. And this is more even visible in read-dominated workloads. So now, in terms of objects, it's also kind of comparable to hazard pointers. So hazard pointers is known to be very memory efficient. With Crystalline, we were able to achieve the same pretty much efficiency. And finally, for skip list, just kind of were actually even better than all other algorithms, right? For both Crystalline L and Crystalline W. And again, in terms of memory efficiency, it was very memory efficient. Thank you so much. Code is available on my website, and I will gladly answer your questions.